Betelgeuse or creepy crawly juice is a red monster star. In the event that you put it where the Sun is, it would stretch out to the orbit of Jupiter. It's truly shaky and is going to detonate. Examining the baffling insect juice at its core, new research has uncovered peculiarities that go against our current knowledge of star activity. Despite its huge size and looming cosmic explosion potential, researchers have been confounded by insect juice's erratic darkening patterns. This is an example of rare stellar behavior, as well as a star moving toward the end of its life cycle. Current astrophysical models fail to adequately describe scarab juice's complicated internal dynamics, which are demonstrated by its unevenly throbbing surface. Unlike normal red supergiants, a cloud of dust and gas is conforming to insect juice because of its unbelievable pace of material shedding. According to specialists, this stellar mass loss is much rougher and more unpredictable than what is expected by theoretical models for stars in its group. The results have sweeping implications, suggesting that red supergiant evolution is driven by unknown mechanisms. On top of that, bizarre magnetic activity on creepy crawly juice's surface has been detected by recent observations. This new field of inquiry could be impacted by this movement, which could be influencing the star's mass loss patterns and volatility. Both the observed and predicted magnetic fields are more intricately organized, stirring up doubts about the standard model of stellar magnetism. These new discoveries have researchers reconsidering bug juice's ultimate fate. Although a supernova explosion is expected, the exact moment and type of this disaster are now the subject of heated debate. The characteristics of Betelgeuse's behavior suggest that it may not undergo a supernova explosion in the way currently expected for red supergiants. Some have hypothesized that insect juice's peculiarities might have been affected by an external force, such as a planet or companion star. This has added another layer of mystery to the situation. One potential explanation for bug juice's inconsistent darkening and mass loss could be the gravitational influence of an adjacent celestial body, which would distort its outer layers. Considering these new facts, creepy crawly juice should be viewed as a beacon for rethinking ideas about stellar evolution, not just a case study in stellar life cycles. Grasping the various outcomes of stellar evolution, particularly in the final stages of life for massive stars, might be facilitated by the star's distinct features. Beyond being a galactic spectacle, scarab juice's upcoming supernova is a milestone that could reshape astrophysical theory. An extraordinary opportunity to examine the destruction of a massive star in unmatched detail could be presented by the energy produced by such a supernova, which could be observed from Earth. Among the less studied consequences of insect juice's supernova is its impact on the surrounding interstellar environment. Nearby atomic clouds might be stimulated to form new stars by the shock waves and expelled material, with the potential to provide insights into stellar lifespans. This process, called triggered star formation, could lead to a new generation of stars. Valuable data on supernova physics could be gathered from creepy crawly juice's light curve. Live observation of the explosion phases could either confirm or disprove current predictions, particularly those related to supernova nucleosynthesis, the creation of heavy elements like uranium and gold. This phenomenon could significantly alter our understanding of the distribution of these elements in the universe, which are crucial for the makeup of planets and life. The potential detection of neutrinos and gravitational waves from the supernova is another promising area. The properties of dense matter and the elements involved in the supernova explosion could be better understood with the help of such discoveries, which could open new directions in multi-messenger space science. Additionally, the compact object left behind after the supernova could turn out to be a black hole or a neutron star in its aftermath. Our knowledge of stellar remnants and the final stages of stellar evolution would be greatly impacted by this outcome. Insect juice's supernova might have sweeping effects on the interstellar medium, altering its chemistry and dynamics while adding heavier particles to it. This enhancement cycle is crucial for the development of galaxies and planetary systems. Ultimately, the impact of a bug juice supernova on Earth's environment is an intriguing but speculative idea to consider. While the star is not close enough to pose any immediate threat, the illuminated sky could affect creatures that rest during the day and could meaningfully affect different environments. With everything in question, the last cosmic explosion of scarab juice is something beyond a fantastic sight. It is a perspective change with far-reaching ramifications for the fields of space science and astronomy on account of its unrivaled awareness and goal. The James Webb Telescope has uncovered already obscure intricacies in Betelgeuse's conduct. Among the most stunning discoveries is the identification of better features in the star's outer layers that had not been seen before. The observations showed that the star's breathing is caused by an organization of huge convection cells that move heat from the center to the surface. The complexity of this throb is beyond anything we have seen before. Its size and brightness challenge our assumptions about star elements. With the James Webb's close infrared abilities, researchers have been able to see the dust creation processes around Betelgeuse unfold in real time. Stars come in the grandiose dust cycle, which is important for planet development and life as we know it, and can be better grasped through this process. Red supergiant mass loss cycles can be better understood thanks to the telescope's observation of material launch from insect juice's surface, which captured the introduction of this heavenly dust. Moreover, scarab juice's magnetic fields yielded a surprising finding. The James Webb Telescope has tracked down perplexing designs in the magnetic fields of these gigantic stars, refuting prior suppositions that their environs were somewhat essential. Based on these outcomes, the star's magnetic field is likely influencing its throb conduct and is critical to its mass loss process. Most intriguingly, scarab juice's expelled material shows signs of possible chemical complexity. According to James Webb, it was not thought that particles and perhaps organic compounds could exist in the hostile environment surrounding a dying star. The nature of the particles that can be formed in space and the chemistry that occurs around a cosmic explosion are both elevated by this new finding. Better predictions of when insect juice would go supernova have been made possible by the more detailed observations of its size and temperature that the telescope has provided. Models that attempt to predict the life expectancy of large stars depend heavily on these estimations. But that's not all. Betelgeuse has more to hide. After this first baffling layer, there will be something else to strip back upon further inspection. What did we find underneath its pounding surface? We welcome you to join us as we unveil a universe that surpasses our most out-of-this-world fantasies. Diving into the latest perceptions of creepy crawly juice made by the James Webb Telescope focuses on the star's puzzling nature and ushers in a new era of immense exploration where each new discovery raises more questions than it answers. Among the giants of the universe, insect juice stands out as an unequaled observational target for novice and expert stargazers alike. At around 642 light-years from Earth, this star, which marks the shoulder of Orion, can be seen clearly even without telescopes. It is a bright, obviously rosy star. Among the stars, the fact that it is throbbing, which isn't easily seen with the naked eye, further complicates matters while studying scarab juice. It is not just expanding and contracting in a normal rhythm like a heartbeat, but in an irregular pattern that has long perplexed cosmologists. This anomaly causes significant variations in brightness over time, which can be seen with even modest amateur gear. Using advanced observational tools, recent studies have shown that Betelgeuse's size is so progressively unstable that its actual diameter can change by a factor equal to the solar distance to Mars. This discovery raises concerns about the stability of red supergiants and points to a very unstable period in Betelgeuse's life cycle. The star's surface is also decorated with enormous spots, extensively larger than those on the Sun, which cause variations in the star's glow. These spots, which are sites of intense magnetic activity, further complicate the star's throbbing pattern and confirm the wild cycles occurring inside and surrounding creepy crawly juice. A complicated atmosphere surrounding Betelgeuse, consisting of gas and dust being ejected from the star, has been proposed by recent observations, adding to its persona. This material forms a cloud around the star, which is a contributing factor to its changing sky appearance and raises fascinating questions regarding the nature of mass loss in red supergiants. Overall, observing Betelgeuse overhead is a way to delve into the deepest secrets of celestial evolution. The pounding red light gives a stunning scene, as well as a window into the violent life of a perishing star. When stars like Betelgeuse burst into cosmic explosions, Their cores break down under the power of gravity, making either a neutron star or a black hole, depending on the star's underlying mass. This inestimable event is of amazing extent and essentially switches the space around them, adding to the heavenly birth and death cycle. One such result could be neutron stars, which are very dense remnants, about the size of a city but with a mass larger than the Sun. Such objects show extreme attributes, such as strong magnetic fields and fast spin speeds, which result in beats. These electromagnetic radiation emissions are powerful. A black hole can be formed when the mass of the imploding core is large enough. A black hole is an object with such strong gravity that not even light can escape from it. The region around a black hole, where matter is heated and X-rays are emitted before being consumed, is a rich field for galactic observations that shed light on the properties of gravity and high-energy physics. Additionally, cosmic explosions deliver elements heavier than iron into the interstellar medium. These explosions advance the universe with components formed in the core of the detonating star through atomic fusion. These components are the building blocks of planets and, likewise, life. The material shot out by a cosmic explosion mixes with the gas and dust around it to form molecular clouds, which will collapse to produce new stars and planetary systems. Moreover, the shock waves from the blast can cause surrounding dense molecular clouds to implode, which, in turn, can speed up the formation of new stars. This process highlights the interdependence of astronomical events, where the death of one star leads to the creation of others. A star's life does not only end in the aftermath of a cosmic explosion, but it also plays a significant role in the vast cycle of matter, which influences how galaxies evolve and may even spread the seeds of life throughout the universe. Regarding the potential impacts of Betelgeuse's cosmic explosion on Earth and our solar system, it is important to note that, despite the explosion, the star's distance of about 642 light-years acts as a buffer, greatly reducing the immediate effects. However, the event would not go unnoticed and may have various significant consequences. For instance, the cosmic explosion would be the brightest star in the sky for at least half a month, if not months, with estimates showing that Betelgeuse could shine as brightly as a full moon, turning night into day and making itself visible even during the day. This sudden brightness could affect nocturnal creatures, altering their patterns of predation and navigation. In past cosmic explosions, such as SN 1054, which formed the Crab Nebula, and SN 1572, which Johannes Kepler observed, the explosions were bright enough to be considered visible stars during the day. Although these events provided us with much knowledge about cosmic evolution, their distance was too great for them to impact Earth significantly. We can expect Betelgeuse's cosmic explosion to be a magnificent light show, with no obvious threat to our planet. Betelgeuse, with its larger size and closer proximity to Earth, would certainly provide more insights into the mechanics of cosmic explosions, the formation of neutron stars or black holes, and the synthesis of heavy elements. This offers a unique opportunity for scientific study. The last cosmic explosion seen with the naked eye in our universe was SN 1987A in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Regarding cosmic radiation, a supernova should be located within approximately 50 light-years to endanger Earth's biosphere by depleting ozone and exposing the surface to harmful UV radiation. Since Betelgeuse's cosmic explosion is over 600 light-years away, it wouldn't significantly raise cosmic radiation levels on Earth and therefore wouldn't endanger its inhabitants. However, the cosmic explosion might produce unusual objects, such as black holes or neutron stars, whose luminosity would provide a unique context for astrophysical investigations. By studying these remnants, we may learn more about the stellar evolution of massive stars and the properties of these phenomena. If you thought Betelgeuse's pulses were the zenith of cosmic mystery, prepare to dive deeper into the core of heavenly life and death. The story of supernovae is ready to be told, a tale of immense creation and destruction. Are there any deeper implications in these cosmic fireworks? Will we uncover the blast of a star known as a supernova, one of the most impressive cosmic events ever witnessed? Supernovae are significant for the evolution of the universe in many ways, including the distribution of life-supporting elements and the impact on star formation. Two main types of supernovae have been identified, each with its own cosmic origin and implications. Type Ia supernovae involve a binary star system, where a white dwarf star accumulates matter from its companion. When this white dwarf reaches a critical mass of about 1.4 times the Sun's mass, it undergoes a catastrophic collapse, resulting in a nuclear explosion. While this type doesn't greatly enrich the universe with heavy elements other than iron, it is a crucial tool for measuring cosmic distances because of its consistent peak brightness. On the other hand, Type II supernovae occur when large stars that cannot sustain nuclear fusion collapse under their own gravity, expelling their outer layers in a massive explosion. This is a key process in the cosmic synthesis and distribution of heavy elements like carbon, oxygen, silicon, and iron. Depending on the star's mass, the imploding core may transform into a neutron star or a black hole. Type II supernovae are born from these events. Supernovae explosions are known to create heavy elements like gold, uranium, and platinum through nucleosynthesis, a process that is rarely discussed but essential for the chemical evolution of the universe, as it seeds future generations of stars and planets with the building blocks of life. Beyond the creation of elements, supernovae can compress interstellar gas and dust in a process called triggered star formation, which restarts star-forming activity, ensuring that galaxies continue to evolve and remain dynamic. Furthermore, supernovae release immense amounts of energy into the interstellar medium, heating it and enriching it with heavy elements. This enriched medium serves as the substrate for the next generation of stars and planets. Supernovae play a crucial role in the cosmic matter cycle, contributing to an environment where stellar deaths lead to new cosmic objects. The study of supernovae also sheds light on the fundamental physics of extreme conditions, such as how matter behaves under immense pressure and temperature, how plasma shock waves function, and what neutrinos, those elusive particles essential to the core collapse mechanism, are like. Understanding supernovae and their significance not only satisfies our natural curiosity about the universe but also reveals the processes that have shaped the cosmic environment, showing us where all the materials that make up our planet and ourselves came from. Betelgeuse, Antares, and the speculative Mu Cephei are three of the most fascinating and massive stars in our universe, and each brings something uniquely grand to the cosmic stage. Betelgeuse, with a size multiple times that of the Sun. The Sun's range is a red, very massive star of huge scope. Its iridescence, which vacillates a ton, places it in the main 20 most brilliant stars overhead, and this is dependent upon huge variations in radiance due to its throbbing nature. This, related to heavenly winds, gives the impression of a dying star, with a mass of multiple times that of the Sun, and a size of roughly several times the Sun's. Antares is marginally more modest than Betelgeuse, yet no less amazing. Its rosy glow and variable splendor rival and, at times, outperform Betelgeuse, depending on their respective patterns of fluctuation. Antares has a mass around 12 to 15 times that of the Sun, and its own huge mass loss features the diverse results of heavenly advancement. Among red supergiants, they are not to be eclipsed. Let us enter the space of speculation and contemplate Musfie, a speculative star that stretches the boundaries of size and splendor even farther. With a range of multiple times the Sun's, Musfie would hinder the light from Betelgeuse and Antares, shining brightly enough to be seen across the system. With a mass of multiple times the Sun's, Musfie would represent the furthest limits of mass and brilliance among red supergiants. Illuminating the elements and fluctuation of these infinite behemoths, research into the accounts and characteristics of Betelgeuse, Antares, and the speculative Musfie reveals insight into the amazing variety and movement of stars in our universe. The differences in size, glow, and mass among these giant objects overhead highlight the complexities of heavenly development, while at the same time serving as a sign of the dynamic, ever-evolving nature of the universe. Contemplating what will befall these stars helps us understand that each star's story is a singular journey, contributing to the grand narrative of the universe, a story that continually changes our view of the cosmos and our place in it. We have seen the variety of the universe as we have traveled from Antares to Musfie. However, the question remains, what fate awaits our giant? The answer could change our perspective on the night sky forever. Betelgeuse remains as a mammoth amidst the stars, but it is not alone in its vast dance. Stellar evolution is a complex cycle that contrasts greatly with star mass. By contrasting the eventual fate of our Sun with Betelgeuse, a massive star, we can see the various outcomes of heavenly life cycles. Red supergiants like Betelgeuse are approaching the end of their life cycle, which is characterized by a dramatic supernova blast instead of a serene cessation of heavenly activity. This catastrophic event happens when a star of this mass has exhausted its nuclear fuel and is no longer able to withstand the inward pull of gravity. For Betelgeuse, whose initial mass was estimated to be 10 to 15 times that of the Sun, core collapse is inevitable, and a supernova will result, leaving behind either a neutron star or a black hole. On the other hand, a medium-sized star like the Sun will undergo a significantly less violent death. It is currently in its main sequence phase, progressively fusing hydrogen into helium at its core. This cycle will last for about another 5 billion years. After this phase, the Sun will expand into a red giant, consuming Mercury, Venus, and possibly Earth. Following this stage, it will shed its outer layers, forming a planetary nebula. What remains will be a white dwarf, a dense, cooling remnant of the star it once was, and it will gradually fade over trillions of years. The Sun's future is vastly different from Betelgeuse's due to their differing starting masses. Massive stars like Betelgeuse have short lives and explosive deaths, using up their nuclear fuel much more rapidly than smaller stars like the Sun. Their violent deaths enrich the interstellar medium with heavy elements, which helps form new stars and planets. In contrast, the Sun's slow progression to a white dwarf will have less immediate impact on the universe around it, but its eventual demise will significantly affect the local solar system, particularly the inner planets. An understanding of the heavenly development of stars like Betelgeuse provides insight into the ultimate fate of our Sun and demonstrates how the universe operates as a cycle of matter and energy. The cosmic ecosystem depends on the recycling of materials from star and planet deaths, whether by supernova explosions or the shedding of planetary nebulae. Looking at the evolution of these two vastly different stars highlights the range of ways stars can develop over their lifetimes. All of these processes, however, are governed by the same laws of physics, and their outcomes depend on the mass they started with. These heavenly behemoths, red supergiants like Betelgeuse, are among the largest stars in the system, often exceeding sizes of multiple times the Sun's radius. They play a significant role in several vast cycles, serving as major stages in the life cycles of massive stars, and contributing fundamentally to the chemical evolution of the universe. The chemical development of the interstellar medium is greatly enhanced by red supergiants because, during their fusion, they produce elements heavier than hydrogen and helium, up to iron in the periodic table. When these stars explode in supernova events, they release these elements into space, where they contribute to the material that can be used to form new stars, planets, and even life. This cycle is crucial for the evolution of the universe, as it ensures that future star systems will have the building blocks required for planets and possibly life. It is hoped that the final stages of red supergiants' lives, especially during supernova explosions, provide favorable conditions for the formation of even heavier elements through rapid neutron capture processes, adding to the astronomical chemical variety. This is due to the fact that the cores of these stars are so hot and compressed that they can undergo advanced stages of fusion, which wouldn't be possible in smaller stars like our Sun. Speculations about heavenly evolution and our understanding of the development of massive stars, from main sequence stars to red supergiants and finally to supernovae or directly to black holes, present new challenges and refine existing theoretical models that must account for mass loss, variations in brightness, and the complex interactions of nuclear processes that define these giants' lifetimes. Red supergiants are a significant benchmark for stellar evolution theories because their properties provide critical insights into the mechanics of star formation and death. Also, ways of behaving shed light on this whole interaction, controlling the making of stars. Red supergiants are central members in the unique harmony between heavenly birth and death in the universe, and the supernovae that frequently mark their end of life essentially affect star development in the system. Shock waves from these blasts can pack close-by subatomic mists, which sets off the breakdown of these mists and the birth of new stars. On the other hand, these shock waves can scatter material, repressing star development in specific districts. Red supergiants help in the advancement of information. Finally, red supergiants are logical discovery machines. Investigation into them has pushed the limits of our insight into heavenly environments, wind peculiarities, and the last phases of heavenly advancement. While perceptions of these stars test our biased ideas and move new instruments and approaches in the field of astronomy. Finally, red supergiants, like Betelgeuse, are something other than fascinating objects to see. They play a significant role in the astronomical dance of matter and energy, which influences the chemical creation of the universe as well as the birth of new stars and planets. Astronomers are still speculating about what will happen to Betelgeuse over time, but one thing is certain: it will ultimately transform into a cosmic explosion, an inestimable event that ends its life cycle as a red supergiant. With its current unpredictability and mass loss, Betelgeuse is on the edge of this dramatic change. But when precisely it will happen is impossible to say. Estimates for when its supernova will go off range from any second now to millennia later. An extraordinary opportunity to study the instruments of cosmic explosion events very closely will be introduced by Betelgeuse's looming supernova blast, which will have a significant effect on how we might interpret the universe. Data from this blast could either confirm or disprove current models of heavenly development. Observing a supernova from a star that has been studied in its pre-supernova state would be a first in modern astronomy, giving insights into the causes and sequence of events leading to these explosions. Its supernova blast will be so intense that it might be visible to the naked eye from anywhere on Earth, even during the day, giving a cosmic show not seen for centuries. For a while, it will rank among the sky's brightest objects, leading to the formation of a new star visible to the naked eye. From a scientific perspective, the supernova will provide an opportunity for cosmologists to observe the nucleosynthesis process, which is crucial for understanding the development and distribution of the elements necessary for life as it happens in real time. The forces released in the explosion will synthesize elements heavier than iron. Moreover, the interstellar medium will be affected by the supernova's shockwaves, which might trigger the birth of new stars in nearby atomic clouds. This triggered star formation process is crucial for regulating the rate of star birth and death in galaxies on a larger scale. The heavy element enrichment of the surrounding space by Betelgeuse's supernova will contribute to the ongoing cycle of matter, which is essential for the formation of subsequent stellar and planetary generations, including those that may harbor life. Rehook, we are on the verge of a discovery that could break the foundations of astronomy as our exploration of Betelgeuse and its infinite kin draws to a close. From this story of the giant, what can we learn, and how does it connect to what's coming in the future of our own Milky Way? The final leg of our journey will lead us to the deepest secrets of the universe as we continue our celestial voyage. We enter the mysterious realm of Betelgeuse, a red supergiant star that has captivated astronomers and the general public with its immense size and inevitable supernova. Betelgeuse is a living example of the universe's dynamic and ever-changing nature, as demonstrated by its pulsating breathing nature, as well as its significant contribution to the enhancement of heavy elements in the universe. Through comparison, we have seen how Betelgeuse compares to other massive giants like Antares and Mu Cephei, highlighting the variety and size of cosmic phenomena. We have also explored the possible effects of Betelgeuse's supernova, a stellar event that is expected to light up our night sky with extraordinary brilliance, providing a unique opportunity to study star life cycles and the evolution of the universe's structure. Furthermore, we have discussed the larger cosmic implications of red supergiants, their crucial role in element enhancement, and their contribution to theories of stellar evolution. In addition, we have been able to speculate on the timing and impact of Betelgeuse's supernova, as its inevitable fate promises to add a critical chapter to our cosmic understanding. As we wrap up this celestial journey, it is worth remembering how remarkable Betelgeuse is and how it fits into the vast fabric of the universe. This giant story is far from over, and we can expect new questions and new insights into the mysteries of the universe to emerge before its eventual supernova. If you've been intrigued by the tale of Betelgeuse and the limitless wonders of the universe, then you should consider subscribing for more content. Our vast adventure is far from over, and there are countless secrets just waiting to be uncovered. Join us as we continue to explore space, searching for new discoveries and expanding our understanding of the universe. The next chapter will bring even more revelations, and we can't wait to share them with you. To join us on another cosmic journey, hit the like button, subscribe to our channel, and watch the video on your screen.